Thank you. So welcome everybody. I'm going to talk about the Java language, where the Java language is currently, where it's recently been, where it's going. This is because of the increased pace at which we've been developing the Java language. This is a talk I could basically give at will, and I sort of do. There's always new things to talk about. So I've taken to numbering the talks by the date to differentiate them. So about 4.5 years ago, the world shut down, but we didn't stop working on Java. In fact, I would say that the pace probably accelerated during the COVID shutdown. And during that time, we delivered probably a dozen or so language improvements. Some of which are related to each other, some of which are sort of like point fixes in various places, varying sizes, such. But the list is pretty long, and in fact, the list is longer than this suggests because I have like one line in here for pattern matching, but there were actually like 5 or 6 different JEPs for pattern matching where we evolved the feature, gradually over time. And while each of these features is developed as a standalone feature, it has, its own motivation, its own specification, and it's designed to be self-contained. A lot of these features were designed together and designed to work together. And so as we deliver these features, they enable certain patterns of programming when you use them together that you might not have been able to use before. So I'm going to talk mostly about how these features fit together, because the details about how any given feature works is you can look that up somewhere. So one of the things that really changed quite dramatically about how we evolve the language and the platform is back in the old days, like Java 5, 6, 7, 8 days, we would do these huge sprawling features in basically one go. This was a tremendous amount of work, a tremendous amount of risk. These things often took longer than than we expected they would. When we did changes like generics or lambdas, they came not only with language changes, but also significant library changes. And then when these things were delivered, they took a long time for the community to adopt them, because you had to learn about them, you had to upgrade. The upgrades were often often a big deal. And so when we switched to the more rapid cadence about 6 years ago, we decided that we needed to change the way we evolve the language to break these larger features down into smaller features. And so there's never going to be another Java 8. There's never going to be a big bang where we deliver a huge amount of world-changing functionality in one go. That doesn't mean we can't do big features anymore. It just means we're not going to deliver them in one atomic transaction. And so the features that we work on, there may be 6 or 7 different JEPs in flight at any given time, and they are independent, standalone, but they're not independent. We're designing them together. We're designing them with an eye of what are we doing next. We're ordering them often based on this future feature that we want, what does it depend on, et cetera. And so there still is big feature work going on, but it's being delivered in smaller increments. That's been a big challenge for us to learn how to do that. I think we've gotten pretty good at it, but it took a while, to get there. It's also a challenge for developers, because you don't have these big events like all of a sudden Java has generics or Java has lambdas, which are motivate you to go buy a book, read it, take a course, et cetera. The features, they come out, a little bit here and a little bit there, and it's sort of diffuse, and you don't have necessarily a cue that you should go do some additional education. And so I think it's harder for people to keep track of where things are and where things are going. We haven't changed the principles that we use to evolve the language. So we still care tremendously about making code readable. We say reading code is more important than writing code. People ask us to do features that are mostly about writing more concise code, and our first question is, does that make the code easier to read or harder to read? Sometimes the answer is one, sometimes the answer is the other, but if it makes the code harder to read, then it's not worth it. And we haven't changed our view on compatibility. You only get one chance to break your promises before you lose the trust of the community. And one of the reasons why Java has been so successful for many decades is that by maintaining compatibility, we're not invalidating the investment that people have made in writing Java code and in learning how Java works. The Java code you wrote 30 years ago still works. And that's a huge thing, because it means that people can upgrade at their own rate when it makes sense for them. And because we don't want to be saying, oh, we made a mistake, we're removing this feature from the language, we have to pick fairly carefully what things we put into the language. So let's talk about some of the language features we've done in the last 5 years. I'm going to start with records, which is a feature that was delivered in Java 17. So it might be old news for some people. So how many people here are developing on Java 21? 17? 11? 8? Older than 8? All right, I'm glad there's only a few people in the older than 8 category, but the people who are stuck on 8, come into the future. So what are records? A record is a class that models a nominal tuple. It models a nominal slug of data that has types and it has names. And so there's an example here of what a record declaration looks like. I say record point, open paren, int x, int y. That's saying I'm declaring a class called point. So that has a name, nominal, and it has two components, int x and int y. They have names, x and y, nominal. And this is an immutable carrier for the state description, int x and y. We derive the obvious API, constructors, accessors, equal hashcode, toString, etc., from the state description. But they're regular classes. They're not some special little thing. The curly braces, the open-close curly braces, they happen to be empty, but that's the body of a class declaration. And you can put methods there. You can implement interfaces. You can do a lot of the things that you can do with a regular class. And so, we compare them to tuples because people kind of understand what a tuple is, but they're classes, and they interoperate with classes the way you'd expect, and they have all of the benefits that classes have. Now, a lot of people like records because they reduce boilerplate, and they do, but we didn't do records for that reason. We didn't do records because code concision was the important thing. The important thing was the semantics about what a point record is. A point is X and Y and nothing else. That's a semantic statement, that this is a carrier for, we say the data, the whole data, and nothing but the data. By making that semantic constraint, you get a bunch of boilerplate advantages, which is great, and people like how concise they are. But the way we look at that is get the semantics right, and the boilerplate will follow. Don't start with the boilerplate, because all you're doing is adding new complexity by having multiple ways to do the same thing. One of the things that people don't immediately know about records is that they're actually safer than ordinary classes. When you serialize and deserialize a record, because we know the structure of the record, it's there in the header declaration, when we deserialize a record, it goes back through the constructor. So if the constructor is validating the arguments and someone forges a serialized instance that has invalid arguments, it'll get rejected at deserialization time because the constructor is going to throw an error. And so in addition to being clear and concise, they're also safer. So, okay, what aren't records? Before we had records in the language, a lot of people said, we want tuples, give us tuples. How many people here said that? A few, okay. Tuples are great in languages that already have structural type systems. So in languages whose type systems are primarily structural, a tuple of int and int is a perfectly reasonable type. But everything else in Java is nominal. It's about names. And there's a reason for that. Names are useful. Names help you read the code. Saying point is more evocative than tuple of int and int. Saying, point.x is more evocative than saying point dot the first element. And so you can use records to declare types that are more readable and therefore harder to misuse. This is the same move we played in Java 8 when we did function types. Everyone said, you should do structural function types. And it turns out that the better answer was to do nominal function types, and because that fits into everything else about how the language works. Like I said, a lot of people like the concision of records, but records aren't a syntax generator. Very deliberately, there are no knobs for, I want to control how it generates the code. It's not Lombok. It's a feature for data modeling where you get to say, this class is this block of data, and the compiler enforces that the API can't diverge from the state description. And in fact, there is a very strong contract that's required by the record spec, which probably no one has read, that says if you take a record, you decompose it with its component accessors, you feed those back to the constructor, it had better be equal to the thing you started with. This is actually a fairly strong semantic constraint that allows us to derive a lot of interesting behaviors from records. Okay, so I want to talk about another feature that we did in about the same time period, which is related to records, although it's not obvious from the outset, which is sealed classes. So a sealed class limits what other classes can extend it. It's kind of a generalization of finality. A final class is one that can't have any subtypes. A sealed class is one that can't have any subtypes except for the ones you name. So when you declare a sealed type, there's a permits clause in the declaration where you say shape permits circle and rectangle, and that's it. Nothing else can extend shape. If you define them all in the same compilation unit, we can infer the permits clause, and you don't have to write it out explicitly, which is nice. But the point of sealed types is to be able to directly model, an X is either an A or a B, and nothing else. So this is the nominal version of union types, where we're able to say, I'm declaring a name type, and I'm saying this is exactly one of these things and nothing more. And being able to model choices is really useful. It's also really useful when implementing libraries, where you can expose an interface in your APIs, but you can restrict the implementations of those interfaces so that your library code knows the implementation characteristics, and so it's a little bit of it's not as obvious as records. A lot of people see records and they say, "Oh my God, I've been waiting for that." People don't immediately say, "Oh my God, I've been waiting for sealed types," but when you start programming with them, you realize that you have been waiting for them. You just didn't know it. And records and sealed types are actually two sides of a specific coin, which goes under the name in other languages as algebraic data types. It gets its name because record types are also called product types. They're the Cartesian product of their components. And sealed types are sum types. They're discriminated sums of other values. And in some languages, this is the primary means of building abstractions. It turns out that the combination of records and sealed types is a very, very rich way to model things. You can model almost anything with it with a great deal of specificity and safety. And so kind of an example of a typical algebraic data type is, let's say we're modeling an arithmetic expression. So you say an expression is either the sum of two expressions, or the product of two expressions, or the negation of an expression, or a constant. You can write that in Java. This is real Java code. You can write this really concisely in Java by saying, I have a sealed interface called expression, and then here are the things that extend it. There's 4 records, and a sum has 2 sub-expressions, a product has 2 sub-expressions, a negation has 1 sub-expression, and a constant has an integer. We're going to come back to this example, but I first want to talk about another feature, which, again, not obviously related to records and sealed types, except that it is, which is pattern matching. Pattern matching is a pretty big deal. It's less obvious that it's a big deal because we've been delivering it in very small increments where each of them may not seem all that powerful, but when you look at the big picture, it actually adds up to quite a lot. So pattern matching is a way of taking something we do every day in Java code, which is combining testing something, are you an X, and if that test succeeds, saying, okay, I'm going to treat you like an X, give me the data the X carries. So it combines a test and a conditional extraction. The simplest example of that is a type pattern. So have the old code on the left where you say if X instance of string, so what do? Then I cast X to string and then I use it as a string. Okay, now this code sucks, right? Because you have to do something twice, and that duplication gives you an opportunity to make a mistake. How many people here have made the mistake of you do an instance of test, and because you cut and paste it from somewhere else, you cast it to the wrong type, right? We all made that bug. And it's just the repetition is a bug waiting to happen. So this gets replaced with a type pattern. The example on the right, the type pattern is string S. That's a type pattern. Looks suspiciously like a variable declaration, not by accident. And it combines the instance of and the cast, where you say if X instance of string S, that means is it a string? If so, cast it to a string and bind that result to the variable S. More concise, but more importantly, less error prone. This is the simplest kind of pattern, but patterns can get a lot more fancy. One of the interesting things about pattern matching is it's the first time where a variable declaration can happen in the middle of an expression. So if I say if X instance of string S, I'm declaring that variable S right there in the middle. So an interesting question to ask is, okay, when is that variable in scope? And it turns out that variable is in scope wherever it would be definitely assigned. And it is not in scope wherever it would not be definitely assigned. So for example, in this code, I can say if X instance of string S and S.length is greater than 0, because I can't get to the right side of the and without the left side having succeeded. These are the same definite assignment flow rules that we all implicitly know but couldn't write down. It works exactly the way that you would expect it based on the control flow operators in the language. And if you did a invert conditional refactoring, it still works. You negate the condition, you turn the and into an or, and the scoping still works the same way. It's still in scope wherever it would be definitely assigned. This is one of those things where you read the spec for it, it's really complicated. You open the book and you say, oh, I don't want to read that. You close the book again. But if I didn't tell you this, you wouldn't notice. It would just work the way you expected, and everything would be great. So, okay, let's talk about another kind of pattern, a more sophisticated pattern, which is a record pattern. Type patterns are very simple. All they did was test if something was a particular type. A record pattern combines a type test pattern with extracting the components. So if I have a shape, and circle is a subtype of shape, and I want to say, are you a circle? And if so, let me get the components of the circle. I can use a record pattern, that's the thing in red in the middle, instance of circle, point, center, int, radius. And that says, are you a circle? If so, cast it to a circle and extract the center and radius into those variables. And you can use type inference there. You can say var instead of a manifest type if you want. And this turns out to be a rabbit hole that goes pretty deep because you can also nest patterns within each other. So this is a more complicated example. So I have my circle and point records. Circle uses point in its state, so its center is a point. And I can say if shape instance of circle ... I'll come back to the ... that means are you a circle? If so, cast it to a circle, extract the center and radius. And now I have a non-trivial pattern that's nested inside my record pattern. What that means is now take that first component of the circle and try to match it to the pattern point, which says, okay, is the center a point? Yes. Okay, extract its components, x and y, and bind them to cx and cy. So this allows us to take apart complicated expressions, sort of all in one go, and it either all works or none of it works. And if there are components that you're not interested in, you can use the match anything pattern, which is denoted by underscore, to say, don't bind anything here, I'm not going to use it. So let's come back to our expression example. Let's say we want to evaluate an expression that's described by this algebraic data type. The way we do that is, well, we've defined the thing in 4 parts. So the solution is probably going to have 4 parts. And we have upgraded the switch construct to be able to switch not only over constants, but over patterns. So that I can say, to evaluate an expression, I switch over the expression. I say, is it a sum type? If so, bind its sub-expressions, evaluate them recursively, and add them together. Is it a product? If so, extract the sub-expressions, evaluate them individually, multiply them together. Was it a constant? Okay, extract the constant. That's the value of this expression. So I was able to define this abstraction very concisely as a union of 4 parts, and I can operate on it concisely using pattern matching, and that's always going to have 4 parts also. Now, how many people here know the visitor pattern from the Gang of 4 book? Right? How many people like the visitor pattern? How many people here are uneasily comfortable with the visitor pattern? right? It's what we've got. It sucks, but it's what we've got. Visitor pattern is largely a workaround for the fact that you don't have pattern matching in your language. So if I wanted to do a different operation on my expression, not evaluate it, but symbolically differentiate it, the structure of the code looks exactly the same. To differentiate an expression, I switch over the different subtypes. Is it a sum? Okay, I differentiate the components and I add those together with some expression. Is it a product? I use the product rule. You've probably all forgotten the product rule from elementary calculus, but this is what it is: A times derivative of B plus B times derivative of A. Similarly, negation, the derivative of a negation is the negation of a derivative, and the derivative of a constant is 0. Okay, so it allows us to get the thing that we get from the visitor pattern, which is the ability to write new algorithms over the same data structure without them all having to live in the same place. But it allows us to do it more concisely and without having to sort of design the thing to be visited over. Okay, so why did we do all of this? Well, Java made it too hard to model data. We were always modeling data as objects, and there was all of this boilerplate foofery that we had to do to pretend the data was an object. And the reality is a lot of what our programs operate on is data. So why are we making it so hard for people to manipulate data? So classic OOP is really aimed at modeling complex entities, complex processes, and all of the tools of OOP are designed, to tackle the complexity of real-world processes. And as a result, OOP tends to erect boundaries. We have modular boundaries, we have access control boundaries, we have encapsulation, and we need that in order to manage the complexity of modeling complex entities and processes. But data is not complex. As the way we've developed programs has changed in the last decade or so, we used to build these big sprawling monoliths. And OOP was necessary in the age of monoliths. But as programs get smaller, they tend to be much more data in, data out, and not a lot of complex interaction, complex process modeling. And also, when you write something like a microservice, its input is likely to be something that isn't Java. It's likely to be some untyped language like JSON or SQL result sets or what have you. And so you have to do some mapping from foreign types to Java types before you can operate on the data as Java data. And so these features are designed to make that problem, which we're all solving on a daily basis, a lot easier. Because modeling pure data with objects is cumbersome, but we don't want to give up objects. And so just like records are objects, but they're objects designed for data, we're able to work within the framework, of classes and interfaces and methods and access control, but in a way that's more suited to data. And all these three features I just talked about, record, field types, and pattern matching, they were designed to work together. They may have been delivered over 8 JEPs, but they were designed to work together to make it easier to model pure data. So what is data? Well, the way we should model data, it's often been too hard to, so we don't, but the way we should model data is immutable. Data is strongly typed. Data, it should be impossible to model invalid states. Data should be easily convertible to and from wire forms because usually that's how it comes into our program and leaves our program, is on the wire. If you do this right, these things all conspire to reduce the need for big fancy boundaries. But in order to do that successfully, we have to be able to use idioms that are natural in the language. So that's why we did these features. So as a quick example of applying this to APIs that we wrote years ago and that we might write differently if we could, think back to the Future API introduced in Java 5. It models a computation that may not have started yet, may be running, may have already completed, may have already failed, and the key method on it is get. You call get, and it either waits, or if the thing's already finished, it says, here's the value. Or if the thing has failed, it says, oh, it failed with this exception. And the way we model that is it returns the value, but if any of the other things happen, like a timeout or an interruption or a failure happen, we model those as exceptions. right? And that kind of sucks. It makes a lot of sense when you look at the API, but then when you look at the code you have to write in order to use it, it's really kind of painful because you have to handle all these different cases using different constructs. So you have the happy path, which is deal with the return value, and then you have all these unhappy paths, and then you have to manually merge them into a single control flow, which ends up with kind of contorted code. So if we had algebraic data types in 2004, we would have had a better way to model the return type of future, which is to say, I have a type representing an async return, and it has 4 subtypes, either success, which carries a value, failure, which carries an exception, or timeout or interruption, each of which carry nothing. And we would have said that future just returns one of those things. And then when you were dealing with the future, you could handle all the cases uniformly. You can say, get me the result of the future, and then switch over it and handle all 4 cases with the same linguistic mechanism. And the reason that works is we turned control flow into data. We turned this thing through execution exception, we turned it into returning something that says, oh, when I tried to run it, it threw this exception. And this allows us to use a whole bunch of other tools that we couldn't use before, like, maybe instead of switching over it, I'm going to pass it to another method that's going to deal with it. Because the thing that I got back from future captures all of the possible results, I can just treat it as data and say, here, you deal with this. So this is something that we haven't been able to easily do until recently in Java. Once you get used to it, you're not going to want to go back. Okay, so what did we have to do to make all this possible? Along the way, we had to completely revamp how the switch statement works. And there wasn't a JEP for better switches. There were 18 separate changes to switch in the context of other JEPs along the way. So switch used to be this really lame construct that could only switch over a certain number of types, only use constants in its case labels. It was only a statement, not an expression. It was basically literally copied from C. And it was a very weak low-level mechanism. And we turned it into a much more sophisticated mechanism where it can be used as an expression or a statement. You can have single consequence labels, which gets rid of everybody's worst problem with switch, which is having to say break. You can switch over any type. Your labels can be patterns, not just constants. You can have guard clauses where you say, is it a positive integer? So you match it to the pattern integer I, and then you can subsequently refine the case with an imperative guard. And also there were various gratuitous restrictions, like you could switch over int but not float. So we made some pretty big changes. We also improved the exhaustiveness checking, type checking for switch, so that the compiler can help you say, yes, you've covered all the cases, or no, you haven't covered all the cases. Sealed types give us a source of exhaustiveness information. If I say a shape is a circle or a rectangle, now the compiler knows whether a switch over shape is complete or not. And if it's complete, we don't make you declare a default clause, which sounds like it's boilerplate reducing, but it's actually about increasing safety. If you have a default clause, we can't type check that you covered all the cases you intended to cover. If you don't have a default clause, we know whether you've covered all the cases or not, and we can give you useful error messages about about whether you've done the right thing. So default clauses are just sweeping an error under the rug. Better exhaustiveness checking allows you to have more confidence that your program is correct. And so we we've had this for a long time with enums, but now we have it for sealed types as well. So if I switch over a color, and let's say my color is sealed to yellow, red, and green, the compiler knows that this switch is exhaustive without having to say default. This can get really complicated if you have combinations of records and sealed types. The compiler is really smart about this. So it turns out that this switch example is exhaustive. It would take you about 5 minutes in your head to work out the details of have I covered all the cases? But the compiler figures it out for you, and so you don't have to. Okay, so that's all really cool. Where are we going next? I like to think of these features as kind of a down payment on a more reversible object model. Now, historically, when we put data together, this is often a lossy operation, and then we have to do some extra work to be able to get the data out of an object. And if you looked at record constructors and record patterns, they look almost alike, and that's not an accident, because we want decomposition to compose in the same way that constructors compose. So we're getting this now for records. Soon we'll be getting it for all classes. But part of the goal here is taking things apart should look like putting it together, because if these two things look differently, that's a place for bugs to hide. So as an example, if I want to make an optional of a shape, I can construct a shape with a factory and then wrap it with the optional factory. These two APIs don't know about each other, but they work together just fine. The way I would take it apart using today's API looks nothing like that. I have to do one thing to take the optional apart, and then I have to do some shape-specific thing to take the shape apart, and I'm probably going to get it wrong the first time. What I want that code to look like is having a pattern that says, are you an optional, which is present, that contains something that matches the shape.red ball with radius 1? Because when taking it apart looks like putting it together, code is less error prone and much more readable. So that's kind of where we're going with that. I have a few more minutes. I'm going to talk about one or two more features. There's a long list of things I'm not going to be able to talk about. I'm kind of amazed I've squeezed this into the time we have available today. I've been talking pretty fast. So this is a totally different feature, which we call paving the on-ramp. How many people here remember your first day of learning Java and your instructor said, public class foo, public static void main, and you're thinking, why? And the teacher says, shut up, you'll know that later, right? This is a terrible way to teach things, right? We kind of throw people in the deep end of the pool and we say, well, don't worry about that water that's coming up to your nose, right? So the first program we encounter is full of concepts that are useless to beginning programmers. They're all about structuring big programs. Access control, classes, statics, interacting with the command line. These are all things that you don't need in your first program. And the student looks at this and says, I can't even find my program from all of this boilerplate goop. And this makes people think, gee, programming is hard. Java is hard. And it's not nice for teachers either, right? Because teachers are constantly having to say, oh, you'll understand that later. No teacher ever wants to say that. Right? That's kind of the admission of failure for a teacher, right? And so all of these features really come from things that Java does to make big programs easier, but they make small programs harder. So we have, modeling with classes. What's a class? Oh, you'll understand that later. We have access control. What's access control? Oh, you'll understand that later. Static versus instance. Command line. What's a command line? Most students have never seen a command line, right? What's an array? And then what is this system.out? What's system? What's out? They turn out to be different things, right? So this is all a lot to throw at students on day one. A lot of these things aren't necessary for simple programs. And so what if we just didn't make them required? So if you're not interacting with the command line, do you really need, to accept the command line arguments? Do you really need to say public? Do you really even need to say static? Do you really need to qualify print line with a class qualifier and a field qualifier? Do you even need to have a class, right? For the first program, really this is all you need. And that's a lot more what it looks like in languages like Python, right? And this may appear to be syntax and boilerplate, but it isn't really. It's about making simple programs simple. It's about not putting barriers in front of people learning. It's about not distorting curriculums to deal with the fact that students have to deal with these concepts early on. A lot of educators will try to deal with all these concepts up front, and the student is lost because they haven't written a program yet. They have no idea what the point of access control is. And so by eliminating some of this goop from the first program people write, it frees educators to teach Java the way they teach Python today. And the only reason that they don't teach Java like they teach Python is they feel guilty about it. They feel like they're skipping over all the important stuff and they're doing their students a disservice. So, I bring this up not because any of you are first-day programmers. You all probably remember the pain of being a first-day programmer, but we want the next generation of Java programmers to have a good experience as well. So there's lots of other features in flight. This was just a sampling. There are a couple of other JEPs that are in preview now, dealing with some of the gratuitous restrictions around constructors, which bite you every once in a while. A better way to modify immutable data, like records. It happens a lot where you want to take a record and you want to create a new record with one of its component values changed. And you don't necessarily want to have to say, new foo of other.x, other.y, different z, right? That's verbose and it's error prone. And so there's something called a reconstruction expression coming where you're able to say, take the point, treat it as if it were mutable, run this block on it, and then feed it back to the constructor and give me a new point out of it. And that actually works really well. It's built on pattern matching. Not obvious that it is, but it is. And it's something that will work not just for records eventually, but also other immutable classes like value types. Bringing a lot of the goodies that records have to ordinary classes, that's a big item that's coming in the near future. And also, I shudder to even bring it up because I've been talking about Project Valhalla for almost 10 years. It's really finally almost here. I promise you, really. I'm not lying this time. And that's going to bring a lot of goodies that will change the way we think about modeling things in Java. So lots going on. I'll have a different version of this talk next year. Some of the same stuff, some new stuff. We probably don't have a lot of time for questions, but in the 4:30 slot today, I don't think in this room, I think in the MC2 room, I have an Ask Me Anything, where I will take your questions about the Java language or other parts of the Java platform. I really like doing those because even if we had 10 minutes for questions, you'd get 30 seconds to ask your question and I get a minute to answer your question. In the Ask Me Anything format, we can have a much longer form discussion about why was this done this way, which I think is a lot more fun. So I hope to see some of you later. Thank you very much.